So section 3.8 is where we're going to take all of those fancy derivative rules that we've been learning so far and apply them to actual situations. Now, it's the exact same ideas that we've already been talking about in terms of derivatives, rate of change, slopes of tangent lines, that sorts of thing. Really, the best thing to remember is rate of change. Now, generally speaking, when we talk about a rate of change, what most people are most familiar with would be like velocity, how quickly a position is changing with respect to time. So that's really what this physics application down here is talking about. If s, a position, is some sort of a function of t, then the velocity at time t, well, that's just your derivative, f prime of t, whatever that is. And then what is the velocity after 2 seconds? Well, that's f prime of 2. After 4 seconds, f prime of 4. When is the particle at rest? Well, that means when is its rate of change equal to 0? That's when is f prime of t equal to 0. So you have to find what f prime of t is, and then you're either putting numbers into it or you're setting it equal to a number and solving for t. When is a particle moving forward, positive direction? That's just where f prime of t is greater than 0. Draw a diagram. What they're talking about is this here. So if you know where a particle comes to stop, so this one right here, I don't know exactly what the function is, but what happens is at time equals 0, it's starting at a position of 0, and then it's moving to the right, and then after 1 second, it comes to a stop at a position of 4, and then it turns around. And then after 3 seconds, it's all the way back at a position of 0, and it stops, and then it turns around again. Now, if I wanted to find a total distance, which I believe is the next thing, total distance traveled, what I would have to do is I would have to find this, and this, and this, and I know that this is 4, this is 4, and then whatever else I would do. You got to add up all those distances. The absolute value, because there's no such thing as a negative distance. If that doesn't make sense, let me know. I'll answer some questions. Then there's logarithmic differentiation, which we talked about. You can use logarithms to get exponents out of to get variables out of the exponent or other such things, or even just to simplify. Number e as a limit is interesting. The one that I really wanted to spend just a little more time with is linear density. Because everybody's familiar with the rate of change of a position. Everybody sort of instinctively has a sense for velocity and speed. This is the one where things get a little weird. It's still a rate of change when we're talking about linear density, but it's not with respect to time. So essentially what's happening here is you have some sort of rod or a piece of wire, then it's basically what all this is saying is that the density changes depending on the position, as in it gets denser as we move along our rod. You're probably most familiar with what do they call it, homogeneous density, where it's just the same density all throughout. But this is a situation where it's kind of weird, where it gets denser the further on you go. And what they're trying to do is they are trying to find the rate of change of the linear density. So there's a few different ways you can sort of think about this. There's a few different ways you can think about this. But what they're usually going to do with this type of a problem is they're usually going to give you some sort of mass as a function of where in the rod you are. So the mass of your object is equal to the square root of how far along your object you are. So the linear density, at a particular position. That's the rate of change of the mass with where in the rod you are. So if m is a function of x, what you're looking for is dm over dx. And as you can see here, they come out to this. And so when x is 1 in this case, you would just plug 1 into here, and you would get 0.5 kilograms per meter. That's how much mass you're adding for every additional meter at that particular point. That's the instantaneous rate of change. Another type of rate of change that you probably aren't entirely familiar with yet is current. If you're planning on going into physics or engineering, it's going to be really important for you to know electrical stuff and how current works. And this little relationship right here, knowing that current is equal to the rate of change of the charge over time, this is actually what allowed me to answer a physics question in 5 lines that took everybody else in the class an entire page of calculations to do, because I was able to just simplify. What happened was he had the integral of current dt, and I said, oh, well, current, I know that's dq over dt, and the dt's canceled, and so I just had the integral of dq, which is in fact just q, and hopefully you'll understand that at some point when you get into physics. But anyway, it's good to know. But current is just the rate of change of the charge divided by the time, or instantaneous stuff. And again, this is all application stuff that we've already done, really. Marginal cost. Marginal cost is a really important one in terms of business. I see this blood flow one. That one's really interesting for like fluid dynamics, but I'm not like super familiar with fluid dynamics. I just know that the velocity of blood depends on the radius of the tube that it's going through, and anyway. Marginal cost. Marginal cost is another one of those big ideas. They really want to know what is the rate of change of the cost as compared to how much you're making at any given time. So like each additional unit, how much is it costing you? Cost per unit, essentially. And the way that you would do that is you would just take the rate of change of the cost with respect to the production level. So let me see, those are my answer keys. So dc over dx. So if they give you some sort of a cost function, so this is our total cost function, if they're wanting to know what the marginal cost is, what is the rate of change of the cost at any particular production level, you would just take the derivative of that. And then what you could do is you could just put in the production level to find out that, so for this one right here, at a production level of 500 units, it's costing you 15 units per item extra for each additional one added on. And yeah, so that's interesting. But again, this is all application stuff that you've already done. There was one other thing that I want to talk about, speeding up or slowing down. Now, this is something that can be made really complicated, but it's not. Basically, these are velocity functions. Now, velocity and speed are different in that speed doesn't care about a direction. So if we look at this and think in terms of velocity, from here to here my velocity is increasing, from here to here my velocity is decreasing. But if we're talking about speed, we got to think about what's happening here. My velocity is increasing and it's positive. So like if this is a left to right situation, I'm moving to the right and speeding up until I get to this point. And then my velocity is still positive. I'm still going to the right, but you see my velocity is getting smaller. I'm actually slowing down. So I was moving to the right and speeding up, moving to the right, slowing down, come to a stop. And then I start to go backwards. I start going to the left. But what happens is, while my velocity is decreasing, my speed is actually increasing because I went from 0 to, let's say, like negative 10 miles per hour. So what happened was 0, I'm not moving. I speed up to 10 miles per hour to the going to the right, and then I slow down and I come to a stop. And then I speed up going to the left until I get to 10 miles per hour to the left. Well, that's a negative velocity. That is a decreasing velocity. I'm speeding up to the left. If you look at this one, my velocity is positive, but it's slowing down. And then I'm speeding up. And then I'm slowing down. And then I'm speeding up. So essentially what's happening here is anytime you're headed towards 0 from up here or down here, you're slowing down. Because up here, you're going to the right, but you're slowing down. Down here, you're actually going to the left, but you're slowing down. As long as you're headed towards 0 on a velocity graph, you're slowing down. If you're headed away from 0, so this way, you're speeding up to the right. This way, you're speeding up to the left, or forwards and backwards. And then for this one, just keep in mind that this is a position function. So a position function's a little bit different, where I have a big speed and then it goes to 0. So that was slowing down. My speed here is 0, and then it's not 0. It's getting bigger in a negative direction, so it's speeding up. At this point, though, my slopes stop getting steeper and they start to head back towards 0. I'm slowing down. And then they start to get steeper again, so speeding up. So anytime your slope is getting flatter, whenever your speeds are headed, whenever your velocity is headed towards 0, then you're slowing down. If your slopes are getting steeper, then it's speeding up. And it doesn't matter which direction it is, because again, speed is just velocity without direction. Honestly, that should be enough to get you through this section. All you're really going to be doing is taking whatever function the problem gives you and finding the derivative and then doing some calculations. So as long as you know all your derivative rules, you should be okay. And for once, I have actually produced the answer key before I ever assigned it. So the answer key is available to you. Make sure you check the answers as you're working through so that you can see whether or not you're getting it right. If you have any questions, let me know.